So, like I said, yesterday we learned, we reviewed some of what we know about complex numbers. 2 days ago, excuse me. We reviewed some of what we know about complex numbers, and then we introduced this idea, which you just practiced in the warm-up today, of like polar form. And it was exciting and interesting, but it didn't seem yet very powerful. And today I hope you'll glimpse some of the undeniable power that polar form brings when it comes to doing arithmetic with complex numbers. So that's the subject, the entire subject of today's lesson. Let's play around with what we can do in polar form. Let's start with just multiplying, dividing complex numbers in polar form. So let's say you have two polar form complex numbers, call them Z1 and Z2, and associate to those numbers an R1 and R theta for that Z1, for the first complex number, and R2 theta 2 for the second complex number. And now I'd like to consider what would happen if let's start with just what happens if we multiply Z1 times Z2. So certainly we get R1 times R2. We can move that out of the picture. But then we have this like binomial times the binomial that we need to do. So I'm going to multiply it all out for you. You see what I'm doing? I just took these parentheses are around this whole thing. And the R1 and R2 I just pulled out to the front, so that's not a big deal. And then I just multiplied cosine theta 1 plus I sine theta 1 times this guy. And the things that have an I moved over to here. And the things that don't have an I moved over to here. So we have in red the real part in the end, what this will be, and in blue the imaginary part. You can check my algebra if you like. But I've organized it in this particularly nice way, just to illustrate that what are we looking at here. In red, what is that? All of that in red is just what? Yeah. It's the cosine of something. Cosine theta 1 plus cosine of theta 1 plus theta 2. And over here in blue, you get sine theta 1 plus theta 2. Comes out pretty nice. So that's our first result. And if you want to do division, you'd see that the result is established similarly. You could prove it for division. But the big takeaway here is that when you multiply numbers in polar form, complex numbers in polar form, you multiply modulus, you add the argument, right? You add the two angles together from the two complex numbers, which gives a very appealing geometric interpretation for multiplication in the complex plane. Multiplication in the complex plane involves angle addition. Huh?
This is pure beauty.
Thanks, exactly. For division, it works similarly, right? I think you would expect this to be the case, right? That you can work it out the same way we just did. Do this divided by this, and I'll tell you that what you'll get is, again, unsurprisingly, R1 over R2 out front, of course, because you're doing this divided by this instead. And instead of the sum, you'll get the difference of the two angles when you divide. So I'll give you a second to digest that. I mean, this is us just developing this first formula. But just know that in the box, we now have a way of multiplying and dividing complex numbers in polar form. Even though that looks a little bit daunting to look at, in the end, it means something very, very simple. And even though it looks a little daunting, I think you'll find that really what we're communicating here is that this is easier than multiplying complex numbers in rectangular form. Because when you multiply in rectangular form, you have to like FOIL it all out and simplify. It's a little harder.
Mr. Tuesday did it.
Shout out.
No, you said shout out.
Oh.
We're not there yet, we're close.
I just want to recognize my people in the back.
Yeah. So the division is the difference between what and what?
The difference between the angles that you have for your, like if you write, you have, 10 is 70 degrees and 5 is 20 degrees, then when you divide, you'll have 10 divided by 2, or else it's like, oh, front. But then you'll subtract the angles, so that would be minus 20. And your new result will be, whatever this is, 50. You'll subtract the 2 angles when you're dividing. Yes, sir. Anyone still need this?
It's okay, I'll sit.
All right, let's do it. All right, when you're ready, so I'll draw this while you work it out, and then I'll call on someone to tell me what you get.
Scissors? Oh, that's 5 cis.
So we're doing 5 cis 50. I'll plot that. You multiply these two together, though, using what we just talked about. Cis, remember, just means is a shorthand for cosine of 50 plus I times sine of 50. All right, Kevin, when you're ready. We're all ready. We're ready. See? See how painless that is?
Wait, so you multiplied those things
I mean, the formula looked complicated on the last slide, but isn't that what all it was saying? It says multiply our values, add the angles. That's all it says. Now, in the picture, we want to just reinterpret what we're seeing here too visually, remember? So, in some sense, I want you to think again about multiplication as being like a rotation, right? Multiplying by this. When you multiply a complex number by 5 cis 50, what do? This takes a transformation on a point, right? It takes the point you have currently, lengthens it, dilates it away from the origin by a factor of 5, and rotates it by 50 degrees counterclockwise, right? You seeing that? Let's just also say what we mean about I again as well. We had a little discussion about this yesterday. We were having fun with that idea that I is this like thing that rotates by 50 degrees, right, by 90 degrees. So what is the polar form for I? Let's just think about that for a second. What is the polar representation for I? It's 1 cis 90. Isn't that the name for in polar form what I is? It's located at 90 degrees, 1 unit above the origin. So that's what I is. It's 1 cis 90 degrees. So what happens when you multiply a complex number, your favorite complex number, by I? R's, what happens to the R value? Stays the same. What happens to the angle though? According to this formula, you add 90. Well, okay, that should gel nicely with what we talked about yesterday. Didn't we talk about I as being the thing that when you multiply it by stuff rotates at 90 degrees? Okay, well this is a more general principle now we're talking about, right? You should also next ask yourself, what would I multiply by to, I don't know, to rotate 45 degrees or something like that. You can come up with all sorts of nice transformations with complex numbers in the complex plane now, using different rotations of various kinds. All right, well, practice these two. I'll call 2 people up. Just use this. Now we're also doing some division too. See how this goes.
Hey, it's a very nice thing to say.
Make sure you pay attention to the instructions. It says give it in standard form on the first one. On the second one says leave it in polar form. Okay? Give me what it says. We'll pass it around again. We're going to pass it around again. Pass it around again. We'll also pass it around again on Monday, too. Or maybe someone has already been inspired or texted their mom and wants to tell them.
Chase, can you give us more ideas for a circular snack? Because I can't think of anything.
Brown chips.
Like,
I've never seen any like
What if possible? They had chips.
How about Oreos? How about chocolate chip cookies? How about a pie?
how about a sugar cube? But cut in the shape of a
Yeah, that's not a part of why.
Just bring a pie and get some frosting and put the pie in.
What about
It's not nice.
conic frosting.
yeah.
What about Oreo?
What about
Am I right this time? Wait, is this third class? When are all the
Bring in Euler's because
Wait, why don't we have just bring normal class?
if you have a loose mathematical justification, we'll take it.
Nobody likes key lime pie.
I love key lime pie.
Never mind, I'm not bringing key lime pie. I'm giving Can someone bring the thing of the forest? I've always wanted to try that kind of
I'm not gonna cut each napkin. Let's make it.
Can you guess?
So when you're dividing, you would divide and then you that makes sense. Yeah.
Well, actually, technically, everything is
Wow, Brandon, really? Okay. Whoa, slow down, buddy.
I'm going the whole entire steps.
You gotta choke up on the pen a little bit and apply a little more fine motor control. Yeah, there you go. Please.
Look at these calves.
I found even more
Brandon, what?
it just burnt.
Alright, sit down. Alright,
I thought he was drawing eyes. He was smelling liquid.
Alright. Let's take a look at take a look at what we have up here. Okay. So on the first one, do you agree that you get when you multiply here you get 6 and you get for the argument you get just pi when you add those two angles. So and you don't even necessarily have to go here if you want. Obviously this will work, cosine plus I sine of that angle. But also think about the fact that what does this really literally mean when we say 6/6 pi? We literally mean the number that's 6 units in that direction. Well, that number, without even doing any algebra, you know has a name and it's -6, right? So you can kind of maybe think geometrically about these things too. Make sure you're doing that. Down here, I think we're already showcasing, this is correct, right? I think we're showcasing already the power of this kind of polar representation. Why? Can you imagine if I told you z squared over w? Do it. Z is 1 plus 2i and w is 3 minus 7i. Oh, that would be painful, right? Yeah, it would. You'd have to square the top, multiply it out, and then how would you do the division? Well, you have to multiply the complex conjugate.
You know what pain is? Pain is when
It would be more painful than doing this, which is very simple, right?
it's when you don't feel good. Sorry, you know what?
All right.
It's when you
Well, as we squared z, it inspires me to ask an even harder question. What happens when we take a complex number in polar form and raise it to an even higher power? Like, what if we want to take a complex number and raise it to the 4th power, say? if it's in polar form, after our discussion just now, it should be easy. What do? Give me instructions on what to do with my polar form complex number if I raise it to the 4th power. Yeah, you'll have r times r times r, r times r, right? You'll have r to the 4th. What happens to the angle? Yeah, you'll theta, that same angle, theta plus theta plus theta plus theta. You get? So in general, if you take a complex number to the nth power, in polar form, it's just what you said. It's r to the n, and instead of theta, you get like theta plus theta plus theta plus theta n thetas, right? So this is sometimes called de Moivre's theorem.
He just said
De Moivre.
No, but if you say it like that,
You
it
say it
means
as
Elizabeth's real name.
Frenchly as possible, as usual. De Moivre. I
De
don't know how many of
Moivre.
those letters don't you pronounce, I forget. De moi, maybe you don't even pronounce the V. I don't know. Where are my French people?
it would be like so it's like
You do say the V.
yeah.
De moi. You say it. But no R. No R. Okay, don't say the R.
It's sort of like
Yeah. De moi. Alright, so when you're ready, let's try it with this one. Listen, what we're saying about the mobs is down here. What we're saying is when you take this to the 5th power, say I didn't even tell you to mobs, how would you have done this on the previous slide without this? Well, I think you would have done it correctly, right? You would have been like, okay, well I just need to multiply this by itself 5 times.
Wait, what are the natural numbers again?
1,
2, 3, 4,
2,
and all those kind of
3.
Okay.
So yeah, if you had just done this on the previous slide, you would have done it correctly too. We just need 2 to the 5th, and then you're gonna have 5 or 6 plus 5 or 6, 5 of those. And then obey the instruction. Write the answer you get here in rectangular form. What do you think de Moivre's first name was? Probably like, yeah.
Good one, girl.
No, it's got to be like Jacques or something like that, Francois or something, right? It's actually Abraham. Yeah, it's actually Abraham. Yeah, you can look it up. It's Abraham is his name. Abraham de Moivre. All right, I'm ready. Who will tell me or walk me through? You first give me the polar form and then give me the rectangular form after that. How about my very favorite student? Silence. Agree, class?
Yes, indeed.
Yeah? Yeah, so I gotta slow down, professor. Okay. Negative root 3 over 2 plus I times 1/2. Oh, I'm with you. Negative 16 root 3 is what you said. Got it. Plus 16i. All right, now I just want you to stop and reflect on what we've done there. First of all, that wasn't too bad. In fact, it was so not too bad that if someone had given me the following problem, wait for it. Root 3 root 3 plus I to the 5th. Imagine that someone asked you guys this problem and said, here it is, it's in rectangular form, to the 5th power, and I want you to give me the answer in rectangular form. What is this? Even though the question asker gave a question to you in rectangular, wants the answer in rectangular, makes no mention of polar, you still might, in fact I think you've now seen that you definitely would, I think you might want to do this, right? Even though it came to you in rectangular form and we desire the answer in rectangular form, I think you might want to go through polar land to do the arithmetic. Do you agree? Because it's so convenient. Yeah? In fact, I mean, you could race this on this, right? See how fast you can multiply this out longhands.
But wouldn't it have to be the same person because we need to control variables?
Wait, what's up?
Isai, why don't you do both of those?
No, I can't do either.
I'm glad. Thank you for your contribution. Appreciate it. All right. So with that in mind, let's keep that in our heart as we think about how we might solve this problem, which is given to us in rectangular form, and asks for a result in rectangular form. And yet, what might you still do? Well, you might convert it to polar to do the arithmetic. So do it. Do it. Now, what's r here? What's r? Some of you are like doing, okay, square root of, it's just 1, right? Like, move along.
Wait, I have a question.
Yes, sir.
Why is it 1? Just curious.
Why is it 1?
Wait, it's a trait ratio. Never mind.
Yeah, those are,
Yeah.
you're good at recognizing things that are on the unit circle. Okay. Francis? Hey, wait, hold up.
What you get?
Can we hear what Francis said again? Sorry.
Is having an exponent not considered standard form anymore?
Right, once it's in, yeah, right, exactly. I mean, standard form is something real plus something real times I.
No exponent.
Something real plus something real times I. All right, so what is the, so what is the polar form for this? 1 cis 3 pi over 4. Okay. So then what do we get? Oh, let's labor to take it to the 4th power. Oh, it's so hard. Not in polar form, it's just what? That was hard. Okay, there we go. And then, again, we might just think about where this is, or if you want to actually think about what the cosine and sine are of 3 pi, you can also just think like, okay, we're pointing in this direction 1 unit. Where are we? -1. Not too bad, right? Pretty painless. Now I want you to recall on Wednesday when I made you do the practice on complex numbers. There were 2 problems in particular. Do you remember? It came out kind of nicely, suspiciously nice. 8, remember? And 64i. Now go back and revisit those if you like, and just see like what's under the hood on those. That's what's you'll now recognize that if you were to do those again, maybe you would have used polar form. Maybe. Okay? Remember that worksheet we did? Okay.
You alluded to that.
I alluded to it maybe. I want to also point out on this problem that that it's a lot of you, if I ask like, what are the square roots of -1, would say immediately, because you know your complex numbers, you're like, oh yeah, plus and minus I are the 2 square roots of -1, right? Aren't those the 2 things that when squared give you -1? You call those like the roots of -1, I and -I. But what you don't know, maybe off the top of your head, are what's the 4th root of -1? Well, there are 4 of them, and one of them is this, right? Apparently, because when you take it to the 4th, you get this. So you just have met for the first time one of the 4th roots of -1. Yeah.
So when you were doing the cis 3 pi over 4 to the 4th, when you multiplied the 4 by the r value, why is it still equal 1?
It's not. You're doing what? Someone correct him.
Oh, you power it.
Our part is the power data.
Power it. Okay.
So like they multiply the 3 pi over 4 by 4, right?
Yeah, it's 1 out front, 1 to the 4th.
Okay.
Yeah.
And then 3 pi over 4 times 4.
Okay, yeah, right. Okay, well, are you ready? Emotionally? For an amazing fact? We have to unfortunately present this right now without proof, but this is one of perhaps mathematics' most breathtaking results that we have to offer you right now. This is the place to put it in this course, I guess. You know, if you're going to say it somewhere, this course isn't the time to do it.
Will we be tested?
No. Are you ready? You guys, I don't think you understand. This is the kind of thing that when mathematicians are asked, professional mathematicians are asked to name their favorite equation, their favorite result, the most beautiful piece of mathematics. This is the one this is often what they say. Are you ready? Are you really? Are you ready? You're really ready? I know, that would be good timing. What? That's an E. That's E. Euler's constant E.
Oh yeah, e to the pi I equals negative.
So this is called Euler's equation, and this is just another way of writing the thing we've been writing the other day. So you could call it polar form still. The R you could kind of just drop out, but the important thing you're noticing here is that E to the I theta is equal to cosine theta plus I sine theta. So that's another way of writing, cis theta instead. You could write E to the I theta. Now why that works we'll reserve until after you've learned some more about infinite series. But the result is still suspiciously similar to what we had been doing. In fact, as you've been doing multiplication today, what have you really been doing with the angles? Adding. When else in mathematics are we asking you to multiply two things and really you're adding? Exponent, right? When you're multiplying exponents, right? When you're multiplying two things, what do you do with the exponents? You add the powers. So the fact that this can be thought of in terms of exponentiation should perhaps not be a surprise. Perhaps that was always lurking there the whole time. Now, of course, we invite you, as some people have already murmured about, to let theta in this equation be pi. And I just would like to have you tell me what you get. When?
-1.
What is the cosine of pi, and what is the sine of pi? I mean, really the powerful result is the one in the box. But this is the one thing that this is a result that's beautiful enough that people talk a lot about it. What do you get here? Of course, sine pi is 0, so you just get -1. So, and sometimes people write it this way because it also looks nice. So you've probably seen this before. This is sometimes called Euler's identity. And if you're looking for like an excellent first tattoo or something, I mean, come on. Look at that. All five of the most important mathematical constants in one small location. Have a great day, you guys. Please do your homework. I love you. Have a good weekend.